Welcome. This is chapter 3.3.3, and we're going to be looking at solving logarithmic equations. So the first thing we're going to do here is just kind of start out with a quick little review here. So we're going to actually just discuss, our log graphs. We graphed logs here in one of our recent sections. So let's just do a quick recap on that. There were three characteristics that we said that every log function in this form had. One of those, remember, was we had a vertical asymptote that ran down the y-axis. So drawing that in, hopefully you can see that there. We said that every one of those log functions in this form here crossed through the point 1, 0. And then they all had a point at, the point b, comma 1, right? So whatever the base is there, we always had a point at 1 there. Because I don't really have a base there, like let's say this was like log base 4 of x, we know then we would have a point at 4, 1. So I'll just throw that one on our graph here. So our function would look something like this. We just come up, hit there, and then curve exponentially go out this direction there. All right, so first thing here, we want to kind of recall what is the domain of a logarithmic function. Well, our graph does not cross the y-axis, right? There are no points at 0. So we're going to say here, basically our domain that we're looking at is all of our x values have to be greater than 0. Okay, so how does that kind of come into play? Well, in class, here we just did a warm-up here and looked at a problem where we had log base 2 of 17, and we had log base 2 of negative 17. They asked you to come up with those values. Many students typed them in on the calculator and said, well, this first one here, they gave me an answer that was, I don't even remember what it was right off the top of my head here. I got to retype it in on my calculator off the screen. We had log base 2 of 17 was about 4.087, right? So x is approximately 4.087, and then everybody said, well, the second one doesn't work. And then we talked about why. Why doesn't it work? Well, with this first one here, we could take this and rewrite this in exponential form, right? By going 2 to the power of x equals 17. But for the second one here, when we do that, 2 to the power of x equals negative 17. Well, that's not going to work for us, right? Because I can't take 2 and multiply it times itself or divide it by itself over and over and over and get a negative answer, right? We can't get a negative answer there. And part of that reason why is when you think about this graph here, right? All of our input values in our domain have to end up being positive numbers. Therefore, we will not ever end up with this negative value here. Our x that we're looking at is always going to have to be a positive number. That's really important to remember as we're solving log equations. So let's jump in here. Okay, so yesterday we solved a lot of equations and we looked at changing them from exponential form into their log form. Okay, today is kind of going to be almost the opposite. So the directions state, solve each equation, give the solution as an exact value and then as a decimal when appropriate. It says, be sure to check for extraneous solutions, which are like domain errors. Okay, so remember, if you forgot what an extraneous solution is, this is when we take the time and we do the algebra all correctly and we get an answer, but then when we plug it back in, it doesn't work. It doesn't make the statement true. So we'll see some of those as we're going through and we'll talk about them when we get to them here. So the most important thing here, and hopefully you have the sound on, okay, this is the most important thing here. When you get a log equation, you need to look at how many logs are there and which sides. are they on? Okay, you could either have, just in this case here, I have 1 log on one side. So anytime we have just 1 log on one side here, we can take this and we can rewrite it in its exponential form, right? We'll say 3 to the negative second power is equal to x. And then that's pretty easy to do. 3 to the negative second power is 1/9. So therefore we get x equals 1/9. Now if we think about plugging that back in up here for our x, we can totally do that because this value is greater than 0. So we're allowed to have that in there. The second problem we have here, it's also a log equation. And this time you notice our x moved. It's now down here in the base, right? But this isn't really going to change much about how we're going to solve this. We're going to go ahead here and say x to the negative second power is equal to 3. So when we rewrite that in its exponential form, x to the negative second power equals 3. Okay, this is going to change what we have to do to solve it. We're going to have to do a little bit more work. Remember, x to the negative second power is like saying 1 over x to the positive second power. And we can kind of create a proportion here. We can cross multiply, right? Cross multiply here, and we're going to end up with this statement here that 3x squared is really equal to 1. We'll divide each side by 3. So x squared is equal to 1/3. Now when we take our square root of each side, remember the square root of x squared is the absolute value of x. And that equals the square root of 1/3, which means that x should equal positive or negative square root of 1/3. Now we do have a problem with that though, because if we took these and plugged these back in, right, if we thought about it, we have log of, we have our base square root of 1/3 of 3 equals -2. That one's okay. But when we try to do the second solution, log base negative square root of 1/3 of 3 equals -2. This one does not work here, right? It doesn't work because we cannot have a negative base on our logarithm here. So in this case here, our answer that we get is going to be just x is equal to the square root of 1/3. That is our solution. And that would just mean that this here, this negative square root of 1/3, is our extraneous solution. All right, so moving on here. Next one, again, we have a log equation. We have just a single log on one side. So again, same procedure. We're going to take this here and we are going to go ahead and change it to its exponential form. 2 to the third power is equal to x squared minus 1. That's 8 equals x squared minus 1. So 9 is equal to x squared. So with this one, we're going to go ahead and take our square root of each side. We have the absolute value of x is going to equal 3. So x equals positive or -3. And now we need to take those and plug those back in to check to see if it makes it true. So when we do that, we'd have log base 2 of 3 squared minus 1 is equal to 3. And when we simplify that down, that's saying log base 2 of 3 squared is 9 minus 1 is 8 equals 3. So that's perfectly fine. And when we do our -3, when we plug it in there, we've got a -3 squared minus 1 equals 3. Well, you notice there, -3 squared is 9, minus 1 also gives us 8. Therefore, in this case, our answers are both positive and -3. And this is why you have to plug the values back in to make sure that it makes this value a positive number. If it's a negative number, we'd throw it out. But just because that number is negative doesn't mean that this whole entire value is going to be negative. All right, we're going to actually jump ahead here a slide or two. Okay, so I want you to go, this one might be on the back of your notes. But what I want to focus on here is now we have 2 logs on the same side. Anytime we have 2 logs on the same side, our goal here is to rewrite as 1 log. So we can use our log properties here. We have log base 4 of x plus log base 4 of the quantity x minus 3 equals 1. Well, since we have 2 logs with the same base here, and we're adding, we can use that property here. We're going to multiply the 2 values together. So this would be like saying log base 4 of x times the quantity of x minus 3 equals 1. Or if you want to, you could go ahead and just distribute that x through and have x squared minus 3x equals 1. And now this becomes a log equation with 1 log on one side. So we're going to solve it just like we did on the other one there, right? On the previous slides. We're going to rewrite this in exponential form. There's your giant spiral, or your around the world. So we have 4 to the first power is going to equal x squared minus 3x. We'll go ahead and set it equal to 0. So 0 is equal to x squared minus 3x minus 4. That should factor into x minus 4 times the quantity of x plus 1. So x equals 4 and x equals negative 1 before we go through and check it. So when we take this x equals 4 and we plug it in, right, we'd have no problem with the log base 4 of 4 plus log base 4 of 4 minus 1, right? So both of those are fine. They both have positive values in here. When we try to do our x minus 1 in there, obviously log base 4 of negative 1 is going to already mess that up. So the x cannot equal negative 1. Our answer for this equation then is going to be x equals 4. Negative 1 is an extraneous solution. All right, now let's jump back a couple slides here. I think this is it. Yep. Now we have 1 log on each side. Okay, and there's nothing else happening there. This one's going to be very similar to like when we were solving exponentials and we said something like 3 to the power of x is equal to 3 to the power of 4. And then we would say, well, since the bases were the same, we were just going to end up comparing the exponents there, and we get that, x equaled 4. It's like we dropped the bases. Same kind of thing happens here. If we have log base 7 of x, we have log base 7 of 2, okay? Well, in order for this to be true, this number has to be the same as that number right there, right? So we can drop our logs, and we get x is equal to 2. The next problem here, again, we've got logs on both sides, but on our right side here, right, we've got more than 1 log. So just like we just talked about, we must first rewrite these as 1 log. So let's take care of these using our log properties. Remember, the first thing we have to do is we got to move this coefficient, this 2, back up here as our exponent on our 3. So we have log base 2 of 3 squared, which we'll just say is 9 now, plus log base 2 of 5. And now since we have this addition in the middle here, that means since we've got the same bases, we can rewrite this as log base 2 of 9 times 5, which should be 45. And we'll bring down the other side of our equation, log base 2 of x. And now that we have it down to just one log, really this part of it becomes irrelevant, right? And we're left with just that x equals 45. So real quick, if I take that 45 and I plugged it in right here, then that would be a positive number. So that works, that checks out. And I didn't check the one before, but if we put a 2 up there, that should make sense. Okay, so more than one log on the same side, we rewrite it as one log. If we have logs on both sides there, we try to get them down to 1, and then we can cancel them out. So this one here, we have 2 logs on the left side, and we have 1 log on the right side. So let's start with the left side here. Log base 7 of x minus log base 7 of the quantity x minus 5. Okay, so that equals log base 7 of 6. Let's rewrite this. So since it's subtraction, we know that's going to be log base 7 of x over x minus 5. And that should equal log base 7 of 6. And now that we have them written here, each with the same log base here, we can pretty much cancel the logs out, and we will just focus on the values. So x over x minus 5 is going to equal 6, and we'll treat it like it's a proportion. Let's cross multiply. So we've got x times 1 should equal 6 times the quantity of x minus 5. Let's go ahead and distribute through. 6x minus 30 should equal x. We'll subtract that 6x from each side. So we have negative 5x is equal to negative 30. So we know that x would have to equal positive 6. Let's check it here, and we plug it in. We'd have log base 7 of 6 minus log base 7 of 6 minus 5. And when that simplifies, that's log base 7 of 1. And this is log base 7 of 6. And you know that this really has the same value as 0, right? Because 7 to the power of 0 would equal 1. So it actually holds true if you want to go all the way through and check it. Log base 7 of 6 equals log base 7 of 6. So x has to equal 6. Awesome. Let's move on here. Okay, we're going to jump back over the slide that we already did. And we're back here at log base 2 of x minus log base 3 of 9 equals log base 2 of the quantity x plus 1. Now, as we look at this here, right, there is something that jumps out at you, and that's as being different, right? This one here has a base of 3, while the other two have bases of 2. But if we look closely at this, right, I have log base 3 of 9. We can rewrite that, right? 3 to some power equals 9. What is this equal to? This would have to be 2. So right now we're looking at log base 2 of x minus 2 equals log base 2 of the quantity x plus 1. Now, very, very, very important here. Okay, very, very, very important. This is log base 2 of x. This negative 2 is not part of that log. Okay, so it's kind of like a separate term. We cannot just cancel out our logs here on this one because we don't have just a single log equals a single log. We have a single log minus 2 equals a single log. So our options are, there's 2 options here for us. So one of these, we can, alter the equation. And our second option will be we could take it here and change it so all the terms are log base 2. So the first one here, right? This alter the equation, all I'm going to do here, right, if I want to be able to narrow down the number of logs I have, I could take this here and I could move my 2 over to the other side, and then I could actually subtract my log base 2 of x plus 1 from each side. So what's that going to do for us here, right, is now I have log base 2 of x minus log base 2 of the quantity x plus 1 equals 2. And because we have this subtraction, right, we could rewrite this now as log base 2 of x over the quantity of x plus 1 equals 2. This now resembles one of the equations that we started with in this section here, right? We have one log on one side, so we can rewrite it in its exponential form. 2 to the second power equals x over x plus 1. Which is like 4 equals x over x plus 1. And now we can just cross multiply to solve it. So we'd have there 4 times the quantity of x plus 1. I'm going to go ahead and just distribute it through since I'm running out of room. Subtract our 4x from each side, so we'd have negative 3x is equal to 4. So therefore x equals negative 4/3. Now when we take that and we plug it back in up here, right, if I put a negative 4/3 in right here, or if I put negative 4/3 in there, we're going to get negative values. So therefore, x cannot equal negative 4/3. That's an extraneous solution. So therefore, we're going to end up with no solutions there. And that's just because the value we got doesn't work back in the equation. We did our math correctly. Okay, so that's one method for doing it, by altering the equation. I'm going to go ahead and just kind of squeeze in that second method for anybody who's interested there. So we could also change, since we had log base 2 of x minus 2, right, we can alter this minus 2. If we think about it, this is like negative 2 times 1, right? Negative 2 times 1. And if you think about that, and I'll do it up here above, because I'm kind of, well, I'll do it on the side here because I have room, right? If I think about it, 1, this 1 could be rewritten as log base 2, right? We have 1 is equal to log base 2 of what? Well, if we think about it, 2 to the first power equals 2, right? So then we would have to have a 2 here. So 1 is the same thing as log base 2 of 2. So we can take this and actually substitute it in right here. Right, and let me finish putting the rest of my equation on there. It was what? Log base 2 of quantity x plus 1. So as we rewrite this, this is like saying log base 2 of x minus 2 times log base 2 of 2. So now what I did here is I created 2 logs on the same side with the same base, and now we can start to look to rewrite this as one log. Obviously here we got to take our coefficient and move it back up here as an exponent. Right, when we do that, that would make this like a value of 4. So we're looking at log base 2 of x minus log base 2 of 2 squared would be 4. And then because of our subtraction in the middle here, we can rewrite this as log base 2 of x over 4 is equal to log base 2 of x plus 1. And now we've got an equation that has a single log on each side there at the same base. So we could just take those values, set them equal, and we've got x over 4 is equal to x plus 1. right? And when you do your cross multiplication there, we're going to end up with the exact same equation that we had right here, and then we can solve it to get, x equals -4/3, but in this case, obviously, again, that's not going to work, so there's still going to be no solutions. All right, so, like I said, there's a couple different ways to do that. There's a couple different ways to do a lot of things with exponents and logs. So you just got to make sure you know how to do at least one of those. All right, I'm tired. I've done a lot of lessons here today, so I am going to call it quits. Hopefully that helped you. If you have questions, bring them to class. Thanks.